Okay, so we got all that stuff, and you were going on about expanding on what it is that you do here at the center.
Right. So my particular research involves growth of 3-5 semiconductors. That's our primary role. We do this using reactors called molecular beam epitaxy reactors. We have 4 of them, and we specialize in a class of 3-5 semiconductors called antimonides. We can also do arsenides, and we also do phosphides. So the combination of these 3 materials means that we can target some very high efficiency solar cells. It also means that we can go after very long wavelength light to harvest it and convert that into energy, and a class of devices that uses these infrared radiations and antimonide semiconductors to harvest energy are called thermophotovoltaic, because typically this kind of light is radiated by hot objects like exhaust from cars, propane flames, and so these are not typically solar radiation based cells, but rather thermal radiation based cells, and that's the distinction between solar cells and thermophotovoltaics.
Cool. So can you explain more what a 3-5 semiconductor is?
A 3-5 semiconductor is a class of compound semiconductors that involves group 3 and group 5 elements of the periodic table. And for instance, here you have a zinc blende 3-5 crystal structure with perhaps the yellow atoms representing group 3. In this case it would be gallium, and the black atoms representing group 5, which could be arsenic, and that would be a gallium arsenide crystal. In this case, this is a slightly different structure. This is also a 3-5, but a hexagonal structure, because it looks slightly different from this one. And this material is called gallium nitride. The group 3 is still gallium, but the group 5 in this case is not arsenic but nitrogen. These are also called compound semiconductors, and the other types of compound semiconductors could be 2-6 if you pick group 2 and group 6. And of course you have the elemental semiconductors, which are semiconductors that are purely made of atoms from the group 4 column in the periodic table. These would be silicon and germanium, both of which are very relevant to the solar cell industry. But they, in that case, you would have a very similar structure, but you couldn't distinguish between the black and the yellow atoms. They would be all the same color because there's only silicon or only germanium in the material.
So what is the process of arranging these atoms in that form? How does one do that?
That's a terrific question, and that's the basis of our research. When you do start the process, you start from a seed crystal, which might be a tiny crystal, and you grow large boules out of it. These boules are typically 6-inch, 8-inch in diameter, and maybe several feet in length. These are manufactured by companies that specialize in pulling these boules. They're then diced into discs, which are wafers. These wafers are now about 350 microns thick, and they can range from 2-inch in diameter all the way to 8 inches depending on your application. We then take these wafers and grow subsequent layers, one layer at a time, on these wafers. So the process of growing something one atomic layer at a time is epitaxy, and that it comes from the Greek word epi, or epithelial, or a thin layer. In this case, it's one atomic layer. And so our reactors typically can grow at an angstrom to several angstroms a second, and an atomic layer might be several angstroms thick. So it takes us several seconds, in fact, to grow one atomic layer of a 3-5 semiconductor, and therefore we can precisely tailor the thickness of our epitaxy to one exact atomic layer. So in many ways, what we do here can be considered the most precise process in one dimension. There's no other machine, to my knowledge, that can replicate a single atomic layer of anything with the precision than that a molecular beam epitaxy reactor can do.
So that reactor, what does it actually do? Is it putting energy and chemicals, or how is?
To a certain extent, yes. So what we do is we have it's a fancy way of spray painting, if you will. So you have ultra pure sources in an ultra high vacuum machine, and the idea is that for semiconductors, for instance, in this structure, one wrong atom in several million atoms could fundamentally change the property of the semiconductor, and thus anytime you decide to grow crystals in a reactor, you have to be very careful about the purity of the material. You do not want stray atoms, and hence the ultra high vacuum. The vacuum inside these reactors are as good as in deep space. So in fact, at one point NASA was towing these reactors behind space shuttles to see if they could get very pure growth. Coming back to the reactor we have at hand, we load the machine up with ultra pure sources of 3 and 5 elements. So in case of the reactors we have at CHTM, we typically have aluminum, gallium and indium as the 3 group 3s, and we have arsenic and antimony in our reactors as the group 5s. And then we have some atoms which are not group 3 or group 5s, and these are called dopant atoms. And we have in one of the reactors we have gallium telluride, and in the other we have beryllium as the dopant atoms. We also use silicon sometimes as the dopant atoms. These are purposely introduced to tailor the properties from of the semiconductor. Now the way the growth really proceeds is rather primitive in some ways. We load these ultra pure metals, and these are 7N pure in some case, which means 99.99999, 7 nines pure. And we load these in very special ceramic containers made of pyrolytic boron nitride, which can sustain very high temperatures. These are then loaded into cells, heaters called Knudsen cells, where the temperature of the winding allows us to evaporate the metal out. So this flux of atoms now approaches your wafer, and the only thing that really blocks it from hitting the wafer is a shutter mechanism. So for instance, if you were to grow a solar cell where you wanted a layer of gallium arsenide followed by aluminum gallium arsenide, then in the first instance you'd open the shutters corresponding to gallium and arsenic, and then you'd open the aluminum shutter as well to introduce aluminum into the mix. So it's rather simplistic. The technology in it has to do with achieving the level of purity that you cannot have organics in, and so all the machinery, the gears have to operate without any oil, which means that it's a difficult process. We use a lot of molybdenum. We bake these machines out to 250 Celsius to drive out water vapor. So there's a lot of complexity involved in achieving the level of purity that we require of our materials.
And these physical structures, then that's just something that the atoms, if they are pure enough, will just form themselves.
So the reason that semiconductors are a special class of materials is the periodicity of the structure. So you notice that this particular structure is highly periodic. It forms some interesting shapes. Now it's a hexagon, and you rotate it a little more, it forms a very different shape. You can look at it this way, again a different shape. So the periodicity of the structure is rather critical. And the whole reason that electronics and optoelectronics work the way they do is because as an electron finds its way through the structure, the periodicity of this lattice introduces some very interesting properties of physics. So to grow something that's a 3-5, you require a substrate that offers the positions of the atom at very particular points. So when we grow in what's called perfect registry, meaning every atom finds its way and sits at that exact same position. Now for instance, an interesting observation is if you want to grow gallium arsenide, you do not have to alternate gallium and arsenic. You just let gallium and arsenic flow on the surface. The bonds are such that only a gallium atom will bond to the arsenic, and the arsenic will only bond to a gallium in return. So you may have a mix of atom, but they find their way in the correct slots, and then they keep growing upwards to result in an epitaxial structure.
Okay, so I have two questions. One, the first one I think is, how do you know that it's in that structure? Do you look at it in electron microscopes?
Absolutely. So there's several ways to do it. And I would classify these tools in many different ways: in situ, ex situ. So we have ways of looking at our crystal as it grows with a very small electron gun. The technique is called reflective high energy electron diffraction. What happens is, when you see a periodic structure any time, and you have an electron come in, the electron wave function, the order of the electron wave function is very similar to the lattice spacing here, or the lattice constant of the material. Therefore, when you send in an electron beam at a glancing incidence, it diffracts. It results in a diffraction pattern, and you can observe that. So if you're not growing something that's perfectly crystalline with a certain periodicity, you will not see the diffraction pattern. So we use that as a general guide to grow these crystals. Now, if you must absolutely see the atomic resolution, we have a laboratory in the geology building, Earth and Planetary Sciences Department, and they have they have some state-of-art equipment to make specimens out of these, and then to look at them with a transmission electron microscope. And a transmission electron microscope again works on the principle of diffraction, but whereas in Reed you looked at a diffraction as a result of reflection, in a transmission microscope it looks at diffraction as a result of transmission. So in that case, your electrons are going through the sample, and that results in a diffraction pattern, which you can then convert to a real image, and you can see the atomic structure, and you actually do see atoms.
Cool. So is that the electron gun thing, is that something that we can maybe shoot? Would that be an interesting process to shoot?
Sure,
or
yeah.
Fake?
Absolutely. No, we could
Okay.
actually, you can actually shoot footage of it.
Okay, that would be really interesting. And
Yeah.
then also, if you have some of those images that we can cut into it.
Yeah, when we do the clean room thing, I can also make sure that Tom has a wafer in the reactor, so you can actually view the diffraction pattern, and it might be good to get Tom's input as well on what you're observing.
Oh, okay, excellent. Okay, so then my second question is the properties of, you mentioned that the properties of this material